Good day, and welcome to the VMS Software webinar entitled OpenVMS Compiler Update. Thank you very much for joining. This is the second in a series of updates we're providing for our x86 product port. We are, of course, involved in our version 9.0 early adopters kit presently. Soon we will be entering into the next phase of our version 9.1 pre-production product, which will be available for all customers, partners, and ISVs. All of this leading to our launch of the version 9.2. We want to thank you again for joining and appreciate the fact that you have great interest in this. It's the livelihood of our company. And so we're excited to be able to provide you these webinars through the virtual world, which many of us live in today. I think this is approximately the 13th or 14th webinar we've done, so by now you'd think we'd have it down, but each one is exciting for us to present to you. And in particular for today, we have our special guest, John Reagan, who has been a long-time OpenVMSer and a long-time VSI employee who's going to be presenting to us. So without further ado, let's go ahead and get started. I would like to make a few comments about the agenda and a few other updates. So again, I will be presenting a couple of points on some general updates since our last webinar was held at approximately 2 months ago. And then John will take things over and has a presentation on compilers and provide you an update on that. And then afterwards, we will have a Q&A session where you can ask us questions in the Q&A box or in the chat box. And we will do our very best to get to all of the questions and answer them to the best of our ability. So let's go ahead and proceed. So since the last webinar, we released our version 8.4-2L3. This is a minor version upgrade. Most customers have the right, as long as they have a VSI support contract, to upgrade to this new version. A couple of advantages here is that for customers who wish to roll up and make the installation of this product easier than our 2L1 version, we've rolled up in a kit, 20 patch kits in a single installable package. Also, another significant advantage is with 2L3, our standard support now runs through 2028 compared to our version 8.4-2L1, where standard support runs through 2024. Check our roadmap on our website for details. And of course, as always, if you have any questions, you can send us an email at either info@vmssoftware.com or sales@vmssoftware.com. Also, since our last webinar, we've added another person to our European professional services team, which is based out of Copenhagen, Denmark. I think between Adam Hoff-Nielsen and Jan Magnussen, who lead up the commercial side of this business for us in Europe, we now probably have an additional, I think it's 5 or 6 members of our professional services team. So we've truly staffed up our professional services team for those different engagements that you may have regarding OpenVMS and other topics. In particular, part of the reason is to make sure we are well prepared to help customers with their x86 migration if needed. We're doing a similar thing in the United States with Dave Sullivan and building up that team here in North America. Okay, so let me introduce John. As I said, John is a longtime OpenVMSer. He is a longtime VSI employee. I couldn't say that a couple of years ago because VSI hadn't been around that long, but we're coming up to our 7th anniversary in the end of July. Time flies when you're having fun. John is a senior compiler architect at VSI, and he will be taking the ball from here and presenting an update on our compiler for x86. Welcome, John.
Well, thank you, Terry. So I'm glad to be here. Most of you have perhaps seen me present other times before. This is, of course, unusual doing it virtual. For one thing, I can't hear everybody laugh at my bad jokes, so we'll go from there. As Terry said, I've been around with VMS for a very long time. I started in 1983 working on the Pascal compiler. I've been involved with VMS compilers since then, other than a short break when I worked in HP Nonstop. I was in charge of the back end when Nonstop was ported to x86, and then I used some of that knowledge moving forward here to bring VMS to x86. So glad to do it several times. Each time porting to a new architecture is a challenge. It's fun. So most of this talk I've used from previous presentations that I've given in the past. I wanted to give some history. Some of this you may know, but to kind of show you how we're going to x86 with our compilers, I wanted to give a little past history to show you what we started with. So on Alpha and Itanium, our compilers have been using a common code generator named GEM. You've heard perhaps spoken of that before. It has a target independent intermediate language and a symbol table, and then the back end generates the code. So, but every front end sees the same back end. Macro 32 was always a little different. It has to know about the instruction set of the target. But we also had macro compilers because at one point, all of or most of VMS is written in macro. Today, probably 20%, 25% is in macro. Along the way in Itanium, we switched to Elf and Dwarf for object, image, and debug data. That made substantial work when we ported to Itanium. The operating system, we had to rewrite major pieces of the linker and the debugger. On Itanium, we switched to an Intel C++ compiler. That was potentially for additional Itanium performance for C++ code. We can argue about whether it actually was a better performer compiler, but it did give a C++ 03 compatible compiler on Itanium. The C++ compiler on Alpha is even older vintage of that. But the other compilers still used GEM. So that's kind of where we started. And then as Terry said, I've been around with VSI since the end of 2014. And the story I'll tell is in the summer of 2014, I was still working at Hewlett-Packard, and I was back in New Hampshire visiting some friends, including Burns Fisher. Many of you know Burns. And so I was going to have coffee with Burns, and Burns says, "Can I bring along Claire Grant?" I said, "Oh yeah, I like Claire. Claire, we worked together on the Itanium port. Claire's hadn't seen in a while, but good." So we show up at a Panera Bread to have some coffee, and first thing I do when they sit down is Claire hands me a non-disclosure agreement, and he says, "Can you sign this?" I just said, "Well, that's pretty interesting for just having coffee and a donut at Panera. I never had to sign an NDA before." So I signed it, and it's like there's a company forming that's going to port VMS to x86, and we want to ask you some questions. And so on the back of the envelope of the NDA, I drew a picture. And that picture, I talked to Claire yesterday, he thinks he still has it in a box somewhere, but I drew this picture for him. And so I said, he was, in the past, the operating system group didn't know much about compilers. The compiler group was separate. We were in a different building. We were making compilers for True 64, in the back in the days for MIPS Ultrix, for Windows NT, for Alpha Windows NT, Visual Fortran. GEM was the Mr. Potato Head, to say the current term, to, you pick different pieces and you got a back end for various targets. So he wasn't sure how this thing even went together. So I drew this picture to show him how everything was at. And I said, everything goes through a common intermediate language and then goes to the GEM back end. I have been through the same picture with Nonstop. The compilers there, not as many, but the same compilers went through a common intermediate language into a back end to generate both either Itanium code on Itanium or x86 code on our x86 board. So I drew this picture and I said, well, how do we go from this to something that we can use for x86? So, they ask about, well, can we move GEM to x86? So, well, it's kind of stale. It doesn't know anything about the 64-bit flavor of x86, 64. But we need to provide compile and go for our customers. Let's pick another back end that gets us there. And our choices were at the time, so you have LLVM, which is the one we picked. It has modern active code base and also has a reasonable license on it. There's GCC, also a modern active code base. If you visit any of the GCC internal forums, it's almost at times like sometimes a shouting match or a Monty Python skit. They sometimes are very argumentative. And there's another one called open64.net, still out there, but it has a pretty low open community and kind of withering. So we went with LLVM. I said, all we need to do is convert the GEM intermediate language to LLVM intermediate language. Easy, he says. And then also to get a C++ offering, I'll back up a slide, we see here with the C++ from Intel, totally bypasses GEM. We needed a C++ solution. So he's asking questions how to get a C++ and how to get all these other compilers to VMS x86 because customers use all these compilers. So I said, well, we can just leverage Clang as our C++ offering the same way we leveraged that Intel C++ compiler on Itanium. We added VMS-isms to it. We can surely do it again, he said. So here's the picture I drew on the back of the envelope a second time for him. I said, well, all we need to do is convert from GEM intermediate language to LLVM intermediate language. I invented something new. It's an empty box. I called it G to L, clever representation, GEM to LLVM. We'd have a new macro compiler, interfaces into LLVM. It also has a backdoor assembler interface, just like GEM did for the Alpha and Itanium macro compilers. And C++ Clang comes with LLVM. They come as a match set. And so use that as the C++ compiler and then add all the VMS-isms to it. So this is the picture, and it's kind of like, wow, this is, this was something to aspire to. And I said, well, we can surely do this. Let's see how hard it would be. So then I joined VSI in late 2014. And here we are today with a lot of people and a lot of work behind us. So I'll go through some of the different things that we've bumped into or are about to bump into. The first question I had to do is, how do I get a LLVM cross compiler running? So which LLVM could I use? Remember, the Itanium C++ compiler is only C++03 compliant. LLVM, even back in 2014, 2015, was already using C++11 syntax inside of its code base. So I couldn't even compile the current LLVM back in 2015. I had to go back to an even older version of LLVM. That was the last one that did not use C++11 syntax, that I can compile it with C++03. So that was, when I asked, that's what they said. 342 is the last one that'll go through a C++03 compiler. I tried, I couldn't get the matching Clang 342 to go through our Itanium C++ compiler. After a lot of asking different people in different forums, my conclusion is that our Itanium C++ compiler is almost C++03 compliant. Clang uses a lot of templates in their C++ code, and I mean a lot, and a lot of specialization of templates. I think they have bumped into a bug in the compiler, but again, I wasn't going to distract myself with having to fix the Itanium C++ compiler just to go forward. So, but all we needed was just the back end, because the first thing we needed were cross compilers for C, Bliss, and Macro to build the operating system. So with having an LLVM now built and sitting there, our next question is, how do I convert that GEM to LLVM? So the GEM intermediate language has, like I said here, close to 300 different intermediate nodes. We had to map them to LLVM. LLVM does not have as many intermediate nodes. GEM has different abstractions. Some were easy mapping. Some were very difficult to map. That picture on the envelope I drew for Claire, I didn't think of all the different issues to come up. So, at this point in the process, I'm going, oh, wow, it isn't as easy as the picture made it out to be, but you know, we chugged our way through it. So currently the G to L phase is about 50,000 lines of C++. It converts all of the gem intermediate language, all of the gem symbol tables, most of the gem debug representation, and converts it all into LLVM equivalents. And then G to L then passes everything to LLVM, and LLVM doesn't know that we're, you know, it's front end agnostic for the most part. So we're just another front end to LLVM, and everything comes out at the other end, almost. And I'll talk to that in a second. And then we will, even on by using LLVM as the code generator on x86, we still will use some of the gem support routines. Gem has a package to process the command lines, to manage listing files, to manage error messages, and it's Gem that writes all the LSC diagnostic files. Gem helps write all the analysis data files. So all that code is just sitting there. It's part of Gem, but has nothing to do with the target. It's just shell-like support routines, and we'll continue to use them going forward. This is, you know, in the compiler world, what happens when VMS now has to meet the new x86. As I mentioned earlier, we already had moved our linker and all these tools to ELF and Dwarf. That is a large step, but everything is platform specific when it comes to object files, right? They're full of instructions. They're full of relocations that are very specific to the architecture. So, you know, changes that were made, we had to make substantial changes to the linker to deal with x86 relocations, something called the global offset table. One of the things about x86 that brought us back to it's like a VAX is that on Alpha and Itanium, every routine gets passed in a pointer to its linker address data. So on Alpha, you heard things called a procedure descriptor. It has a pointer to the linkage section. On Itanium, there's this thing called a global pointer. It has a pointer to this thing called the short section. They're fundamentally the same in principle. On x86, you don't get past anything. The address of a routine on x86 is the address of the very first instruction, just like a VAX. So that was new, but it means that any routine has to know where its addresses have been placed. So when it needs an address for an external routine, it has to know where the linker put it. And this thing is called the global offset table. And the distance from the code to this global offset table is something that is known at link time. And then those two pieces have to kind of move around in as a pair. But that's something that the system has to do. But there's a lot of things we do to the linker. The analyze tool had been enhanced. Debug traceback. Gem only spoke dwarf 2 with some dwarf 3 pieces. LLVM now can handle almost any dwarf. We're asking it to generate dwarf 4, which means there's additional dwarf tags that LLVM generates that traceback and debug will be presented with. Some they can ignore, some they have to deal with. So we had to go through that whole list and make all that code. For a calling standard on Alpha and Itanium, well, on Alpha, of course, it was a VMS-specific calling standard that mimicked the VAX calling standard. On Itanium, we used the Intel runtime conventions, modified them slightly for VMS purposes, but it was an incompatible set of changes. You couldn't take those changes back to an Intel runtime convention like a Linux Itanium and have it work exactly. We didn't want to do that for x86. We want to be upward compatible and be able to not break things and be able to perhaps take our objects to a Linux box or take Linux objects to VMS machines. So we stuck with the AMD 64 ABI and only added one change for an arg count. We'll see here, and that will help in a couple slides on how we're bootstrapping our compilers today. Found out that the memory models don't match well for what is on normal x86 systems. For those who have dug deeply into x86, you either are 32-bit platform, a 64-bit. There's a memory model switch on GCC or Clang. You can tell it that your code and data are within 2 gigabytes of each other, or that your code and data are not within 2 gigabytes, or etc. There's a couple different things. We're moved code to 64-bit address space, but all the static data in the stack has to remain in 32-bit address space. That's due to things like string descriptors that have the 32-bit pointers buried inside of them, or item lists that have 32-bit pointers buried inside of them, or fabs and rabs that have 32-bit pointers buried inside of them. We have a lot of 32-bit pointers that have been exposed in all these VMS interfaces. And to make it easy, you have to keep all that static data that you're going to take the address of in a 32-bit environment. So we have all of those things have to stay in 32-bit space. The other one I don't think I've mentioned here, but with code is in 64-bit space. So I mentioned just a second ago that the address of a routine is the address of its first instruction. How big are code routine addresses? There are several interfaces in VMS that need to, declare exception handler or other things where you need the address of a routine, and there's 32-bit dependencies. Well, the linker will make little small trampoline routines in 32-bit space, and we can use the addresses of those in those instances. And those trampoline routines, they're 2-3 instructions long, will then bounce you to the real routine in 64-bit space. So usually when you talk about, even the code is in 64-bit space, and when you think about the size of a routine procedure value on VMS x86, it's 32 bits. You might be confused in reading through the calling standard on that, but it's because the linker makes these little trampolines behind your back. I think that was one of my distorted ideas, but our next challenge was macro 32 on x86. Macro compiler in general always has to know about target instructions. Gem never had a good high-level interface for macro. Macro has the ability to jump between routines. There's pieces of code in VMS that, a module with, let's say, 100 macro routines, and with the flow analysis, every routine entry point can get to every other routine's exit point. So as far as the compiler is concerned, it's one large routine with 100 entry points and 100 exit points. You could never describe that to Gem. So macro always is different in that regards. But also, macro has to worry about how to map registers. On alpha macro, it presents the 32 bits worth of 32 alpha registers, each in 64 bits wide. On Itanium, we present the same number of registers. We shuffle them around a little bit because Itanium does things like having register 0 hard-coded to 0, so things get moved around. But for x86, there's only 16 registers at best in 64-bit mode, and several of those registers have predetermined, behaviors. You really can't, overtake them. So how do you squeeze 32 registers into a 16 register bucket? You do not. We did try several things, and it turns out that what we finally end up doing is alpha registers are now memory locations that are managed by the operating system. The start of every macro routine actually looks in a special global cell to find where is the address of my registers. And they are per mode, they're per thread. So they're pseudo hardware context, if you think of it that way. They are saved and restored by the operating system at interrupts. They're saved and restored by the operating system across AST calls. They look just like hardware context, but are in memory. And the question I'm sure will be asked, boy, is that a performance issue? It might be, it popped up in front of everything. Okay. So we're writing into memory over and over. The chip's cache is going to help there immensely. But there is probably a memory write overhead at some point. We've done some measurements. It does not seem to be horribly bad. But for a simple macro statement that looks like moval register 1 into register 2, there's in theory a memory read and a memory write. So the macro compiler does try to optimize some things, but that's the solution we ended up into. Now, of course, it prompted us to rewrite more things out of macro into C or Bliss, mostly C. But there's still a lot of macro there, and at this point, I don't see the alpha this alpha pseudo register being a horrible performance at the moment. So macro code for us has been almost untouched. So you can recompile it, and all those things in the macro compiler took care of all those memory references for you. It means, of course, things that have explicit linkages that were passed in between Bliss and C. We have a lot of this code that used to think they had these explicit linkages that were faster than putting parameters in the normal parameter slots. Now it might be somewhat the other way. We've moved some linkages around. We've rewritten some code to go back to standard linkages, that they're faster. Again, on x86, the first 6 arguments are in registers anyway at every call. And so macro seems to be working quite well at the moment. We've had a few little challenges. The other one I didn't mention here are condition codes. x86 actually is an architecture with condition codes that almost look just like VAX, as opposed to Alpha and Itanium, where we had to manufacture condition codes ourselves. On x86, we can rely on the machine to help us in most cases. There are a few dark corners where they're different and got us into trouble a couple times, but I think we've got most of that sorted out, or at least in progress. Okay, so every time I click. So the next was, how does LLVM mesh with VMS? Well, LLVM comes from a world where you're building either for one pointer size. You either have a 32-bit version or a 64-bit version. VMS has a mixed pointer size environment, which means our list of relocations in ELF has mixed pointer size pointer relocations. We had to add that support into LLVM. Not horrible, but we had to add it. There were places in LLVM, I mentioned earlier about memory models, where they thought that code could just always reach into its static data, or one routine, when it calls another routine, that it's gotta be within the same 2 GB address space. I can directly reach that with a 32-bit offset. Well, in VMS, at link time, you can take some routines and put them into one cluster, and you can put other routines and collect them into a different cluster. And for various places, at least inside the operating system, sometimes code is in 64-bit space, sometimes code can be placed in 32-bit space if you need it. And there was places where you can't reach it with a 32-bit offset. You need a larger offset. So everything has to go through the global offset table. There's been a bunch of stuff. Complex linker relocations, how to subtract one relocatable symbol from another. Something you can do in VMS, something that isn't normally done in the Unix world. We've had to add that. Note sections that we use in ELF to encode the module name or compilation date and time. You need those at the link time. You need those when you were specifying linker options files and want to talk about module names. We had to talk about adding an argument count. This is something that doesn't happen anywhere. We have to pass an argument count for every call, even if the prototype doesn't have a ... in it. It's not C oriented, it's every language. I'd had new Dwarf. We'd had new for additional languages that we have in our debugger that you normally don't see in the Unix world, right? You don't see a lot of extra code for Bliss macro encodings in Dwarf on any place else. Again, there's additional exception handling for these VAX pseudo registers, future hooks for machine code listings. Again, I didn't even bother building the LLVM 342 optimizer back in 2014. We were single-stepping code one instruction by a time, and we still are today in many cases. Doing that on optimized code is probably not a good idea. It's very confusing. It would need some additional G to L work. There's some metadata that we have to convert from the gem form to LLVM form for pointer alias analysis. We skipped that just for time savings. And the big thing is, again, I couldn't get it to go through that Itanium C++ compiler that at this point is almost C++ 03 compliant. So working around each of those. Said earlier, we're using the AMD ABI. We're going to use the lib C++ standard template library that comes from LLVM. So it's a match set, LLVM and Clang and lib C++, and the lib C++ ABI library, which is essentially the thing that handles most of the stuff for the C++ try catch statements. It has to know how to decode all the exception handling data. We have a similar situation on Itanium today. We have a standard template library that we licensed from a company, RogueWave, many years ago, and the code that does try catch is a derivative of their code as well. So the mechanism is about the same. We're still going to use the VMS debugger. People have asked me before, well, LLVM comes with the debugger, LLDB, why not use that debugger? I've actually thought about it. We've done some research, maybe someday. It just doesn't handle all the interesting things that the VMS debugger handles. So we've kind of left it alone. LLVM has its own linker. Again, it may be helpful, but boy, the VMS linker knows so much about how to handle options files and symbol vectors and shareable images and protected shareable images and system execlets that a Unix linker has no idea about. We would spend another 2 years adding code to their linker just to make it be the same as our linker. And I said we'll continue to use gem going forward. Then now we're to what we have to do for Clang to make it OpenVMS compatible. Again, on Itanium, we had to add substantial things to the Intel C++ compiler. Here, we're going to have to do the same thing again with making a list. It has to learn about dual size pointers. Fortunately for us, Clang has dual size pointers in it, added by the Microsoft people. They already have, well, it started off as a way to get what they considered near and far pointers, but they really are now 32-bit and 64-bit pointers. So 99% of dual size pointers are already inside of Clang. So we just have to perhaps add a few pragmas or a few command line switches, but it actually is much easier today. Back in 2014, when I said, don't worry, Claire, we can make Clang work on VMS, this dual size pointer thing kept me awake at night. Now, not so much. I've replaced that with other things that keep me awake at night. But we have to teach it, again, how do you get headers from TLB files? How do we get listing files? What additional pragmas do we have to add to Clang to make it work well for VMS C++ applications? Obviously, if you're bringing C++ code from the open source world to VMS, doesn't have any of these things, right? The Clang source base itself doesn't have any VMS-isms in it. It only has one size pointer. So the list is still under construction. We have a good idea. Each time we went from C++ and alpha to Itanium, the amount of VMS-isms got smaller. I think they'll be smaller a little bit again. There are some things that may not have to be there going forward. We're working on the CRTL. All the headers in there may be some language syntax or pragmas that will not be available in Clang. So we are adding some if-def Clangs into all those headers to skip over things or to add additional syntax that is needed on the Clang side. Again, the headers are the headers. We've already been recently enhancing them for C99 compliance in the last couple of years. Not necessarily due to x86, but yes, kind of wrapped in that as well. So, you know, we've been going through the headers several times and we've been adding a Clang to that. We still have questions that we have to answer. Our C and C++ compilers on Itanium, the default pointer size is 32. You have to ask for 64-bit pointers. Even when you ask for 64-bit pointers, long is still 32-bit. That is different than any other C or C++ compiler in the industry. How big is size T? There's issues wrapped around in it for, is it the size of a pointer? But there's an int pointer T type in the C standard that people seem to forget and not use. Everybody thinks that size T is kind of the same as a pointer size. It's not. And since even for our compilers, since we're using a 32-bit stack on VMS, the biggest stack-based variable you'll ever be able to allocate on VMS is 32 bits big. And even then, you're going to run out of stack space and P1 space. So there's places in Clang that we're going to have to look at and be 32-bit or 64-bit pointer, but 32-bit size. So again, we're working through those now. I think we'll come up with some reasonable solution, but we have to worry about existing code moving forward, C++ code from Itanium to x86 on VMS, but also bringing in open source C++ code. So I'm happy to take advice from people, but I've got, you know, there's been, I think I know how big the swamp is. People asking about source code changes we've had to make. There's been almost none. The one that was starting the list is if any C code uses VA lists, the format is different on x86. On Alpha and Itanium, VA list is an array of pointers, array of values. You can copy them with an assignment. You cannot do that on x86. VA lists are a structure that have, I think, 2 shorts and 2 pointers buried into it. It's part of the AMD64 ABI. We just inherited it. It's what Clang knows how to generate. I wasn't going to go into Clang with a 4-foot screwdriver and change it. One thing you do have to do is use there's a VA copy macro built in that comes out of the C standard. We had not put it into our compilers for many years. Looking back, I claim that was a short-sighted decision on previous developers where they had things like VA start, VA end, but never VA copy. We've added that. I think we've even added it to, the headers, and we've even gone through like the CRTL, all the places it does used to do copy of VA lists and make it use VA copy correctly. Didn't mention it here, but one of the things is on VMS, we have both support for varargs.h and standardarg.h. I've been encouraging everybody to switch to standardarg.h. It's a very mechanical transition. At first, we were unable to get varargs to really work well because LLVM doesn't support it. If you use varargs on a Linux box, the varargs.h is pretty much a one-liner that says, like, you know, pound error, this doesn't work, switch to standardarg. And they don't even support it. We've tried. I think at this point, most of varargs actually works as well as standardarg, but I still tell people switch to standardarg, please. We found some places where macro code that called routines that preserved R0 or R1, again, on VAX, Alpha, Itanium, everywhere, R0, R1 are considered scratch at every routine call. There were various places in the operating system that had unusual routines that said they preserved R0 and R1 as I guess a performance behavior. So it lets the calling routine says you can keep things in R1 and R0 across the routine call. Places buried down in the file system in RMS. The macro compiler needs to know that, and it didn't. And then we've seen various places where 64-bit code was writing into 32-bit variables. And we're like, this doesn't work. It's always been broken. Why is that? Well, gem often asserted alignment holes as an optimization. Currently LLVM, and we are building everything no optimize. Remember, so I couldn't even get the optimizer to compile, and it was just going to make it hard to do any debugging. LLVM currently doesn't do anything like adding alignment holes. So the writes overwrote adjacent variables. And depending on what that adjacent variable was, it either was benign or not benign. And we've only seen this in weird Bliss C code that had dual size pointers. You don't see this in Fortran, Pascal, Ada. There's a Freudian slip. COBOL, Fortran, BASIC. So then how do we get to native bootstrapping if that we couldn't build Clang to run on Itanium? So we currently have taken a more modern LLVM Clang on Linux, added a handful of small OpenVMS-isms to it. So we turned something, let's say Clang 10.0.1 into 10.0.1v for VMS. Then we use that 10.0.1v compiler to build it all again, still all in Linux, grabbed all of those objects, brought them back to x86. Remember we said we used a calling standard that is upward compatible from the Linux one, and our linker is now tolerant of Linux objects, and the cross-linker on Itanium linked it all together, and we could then produce a Clang that has native for x86. We did the same thing with the 3 basic libraries that come with LLVM, libcxx, libcxx ABI, and compiler RT, which is their equivalent of our libots for the most part. So that's our process for bootstrapping the very first time. And I'll show you in the status coming up, where are we with this bootstrapping process. Right. I mentioned optimizing. I'll talk a little more about it. So cross compilers always produce non-optimizing code. For native compilers, building Clang and LLVM gets the optimizer, gets Clang, gets all the Clang internal metadata. I believe at some point when we get a native Clang, you should be able to turn on every optimization in that Clang, and it should compile. For the other compilers that use G to L, it's a multi-step process. The better LLVM and now compiled optimization phases should let C or Bliss get some optimization even without G to L knowing about the additional metadata for pointer alias. So that's a work in progress. Again, part of also the reason we didn't do that in the past is the format of this internal metadata for LLVM has changed from LLVM 3.4.2 to LLVM current. So why invent something that we really wouldn't use? So the LLVM interface is under active development. They've made some non-upward compatible changes. We've had to make some changes between LLVM 3.4.2 and LLVM 10. Right, so where are we today? So if all the cross compilers are in place other than BASIC. People have asked, why taking so long for BASIC? So when we wrote the G to L converter, we had the gem documents that describe the gem intermediate language and the gem symbol table. One of the creators of G to L is one of the people who worked on gem, who originally designed the intermediate language and the symbol table. So we went by the book. We found out that BASIC wrote in some their own notes to the side on one of the margins on one of those books. So BASIC did a few things that we were not prepared for. So we've had to go back and revisit G to L and enhance it to add this feature that BASIC used that influences stack layout of stack variables. Gem doesn't provide that interface. basic, figured out how to cheat and trick gem into doing it on previous platforms. And instead of changing the basic front end, we just changed G to L to do it. We actually have Clang running on an x86 box right now. It can compile a good number of C and C++ programs, in the couple hundred count. Nothing big yet, but it's a substantial number of C and C++ stuff. So it's allowing us to do some early prototyping to figure out what works, what doesn't work. Our next stop, of course, is we need to, we can compile G to L with it. That's I think our next short-term goal. But we actually have that compiler running, and once we have all those other LLVM libraries that are out there that are in Clang, we have to. All it takes is getting those gem support routines compiled over. We can compile those. We can compile the C front end or the Bliss front end with our cross compilers. So in theory, we have all the pieces kind of in place to put together native compilers, but we're not quite to that point yet. Debugger has started some early development, but nothing quite yet. Traceback mostly works. So when we start producing native compilers later this year in 9.1, they'll be in stages, and the first ones will be, I've been saying non-optimized, but think of it as, certainly for C++, like I said, we'll get probably all the optimization. For the other compilers, you'll get what you got out of LLVM until we get that additional metadata converted. But that'll be a migration. It'll probably start off as, on the scale of 0 to 10, they might start off at a 3 or a 4, and then work their way up as we finish more code. So at that point, I believe that's the end of my slides. I'm willing to take some Q&A. I think I saw at least one pop up earlier.
John, yes, thank you very much. That was an excellent preparation and excellent presentation and delivery of content. So thanks on behalf of everyone who's attending. Thanks for preparing all this material. As John said, he will be happy to address questions and answers. If you can ask any questions you have, either in the chat box or the Q&A, please do so now. And John, we do have a first question.
I saw that from Nick, yeah, in the chat, yeah.
Yeah, let me.
Okay.
Let me read it.
Yeah, go ahead and read it so we have it in the recording. Yes.
The question from Nick is: are there performance implications from maintaining a 32-bit space, jumping to the 64-bit space?
I don't believe so. Not more than anything you'd see on a Linux box. It's all just memory. So I don't think so. That small trampoline I talked about is indeed a couple instructions big. I'm gonna hope that these modern x86 chips with all their speculative execution, we will ignore things like Spectre and Meltdown for a moment, probably have already bounced their way execution-wise through that trampoline. So I don't think there's a big penalty.
This question from Randy: what standard will the C++ compiler meet?
So it's Clang out of the box, and I think Clang today is already C++ 17 compliant. And I think they're adding C++ 20 features to it now. By the time we get around, so the one we're picking now is LLVM 10. That was just what we grabbed. We'll probably then bootstrap it. Once we have those native, we'll probably use the LLVM Clang 10 on an x86 VMS machine and build LLVM 11 or 12, whatever the current version. So by the time it's probably available later this year, it might even be C++ 20, but I don't know what Clang's schedule is.
A question about the webinar itself. The webinar will be, it's being recorded, and so it will be up on our website in approximately 48 hours from today, so you can review it again. Question from Don: how difficult would it be for someone outside of VSI to port an open source LLVM compiler to VMS? Example, Rust? Question: are there any major obstacles?
So our plan is to, for all of the LLVM changes, I've been attending LLVM conferences, talking to the LLVM community. A matter of fact, if you go to YouTube and Google LLVM John Reagan, I have given 2 presentations in the past, the little 5-minute lightning talks. You can go find those videos on YouTube. They're cringeworthy, but they're very small videos. But all of the LLVM changes, my goal is to push them all back into the main LLVM code base. So at some point you'd be able to download LLVM and have all of our VMS changes already merged into the LLVM. That's only part of this process you need to build it, because you're going to need other tools like CMake and Bash, or at least the GNV package, to complete the steps, because LLVM builds with CMake and either Make, or I don't know if anybody wants to be brave enough and port Ninja to VMS. You also mentioned Rust. I have spoken to people in the Rust community. I think it'd be an easy, not easy, I think it'd be very doable. I think that'd be a great addition for somebody to add to the VMS ecosystem. But so having the VMS version of LLVM, and even if we don't get it into the LLVM code base, we would certainly provide it, ourselves, whether on the kit or on the website. That seems reasonable.
Thanks, John. Question from Mike. Oops, I just lost the question. Do we have any update on the ETA for basic compiler availability in EAK?
I think we're talking about late June-ish, but we're still working through some of the work at the moment.
Okay. Martin writes, will the cross-compiler toolkit be available to v9.1 sites?
I would think it would have to be, yes. I mean, since the native ones get staged, and also I think, just because there's native compilers, I don't expect customers to move their entire application development environment onto their VM. So just because there's a native C compiler doesn't mean that's easy to use. You'll still probably want your cross compilers in some environment to build it.
From Jeremy, can you say in what sequence the native x86 compilers will appear? The statement is, I assume C and macro will be the first.
That would be my assumption. I think we have to build C, macro, and Bliss ourselves. I think once you get past that step, we've seen in the past that kind of hits most of the rocks in the field. Once you do that, I think the Fortran and Pascal and COBOL follow after that pretty easy.
Okay. From Frederick, any information to run .NET Core on VMS?
Boy, I don't know the answer to that. That's something that maybe, Terry, maybe something we can run past Brett.
Yep.
He might have a better feeling for that.
Good suggestion, John. Any updates on the Ada compiler situation?
I did have that Freudian slip earlier.
You introduced the topic, John.
Yeah, I know. I opened the door, didn't I? Oh, I'm going to get in trouble. We, all of us, appreciate that Ada is a very important product for a small but very important set of customers. We are still trying to figure out all the pieces and how to put something together that would be reasonable for everybody. So I can't say anything more than that, but I haven't forgotten about it. Obviously, it's stuck in my brain because I boarded it out.
And I'll add to that we are also, besides from the technical side and the development side, we're trying to also put together, is there a business case for this? So any information that you may have, any of our attendees may have, who would like to assist us with this process in terms of Ada compiler users, developers, please send us an email at info@vmssoftware.com or sales. We would love to put something together. We just need to justify it from a couple of different aspects, as you can imagine. Let's see.
There's some questions in the chat as well from.
Yeah, I know. I'm
Bob
going
and
back and
Alistair.
forth. There's quite a bit. There's quite a bit.
Okay.
So from Philip, I lost Philip. There's Philip. I'm still using the Alpha Fortran compiler, which is F95. I don't think that there is anything substantially newer with regard to a standard support on VMS hardware. What about on x86? Will a reasonably modern version of the standard be supported?
So in the LLVM world, besides the Clang front end, there are people, actually it's SGI and NVIDIA. There's a new Fortran compiler called Flang, the F-Lang compiler. So that is, I think, Fortran 2018 or something. It's very modern. I've been in touch with the Flang people. I've been encouraging them to keep as many of the traditional digital DEC Fortran features in their compiler as well. It's a brand new compiler. They're writing it from scratch. It is part of the LLVM ecosystem. You can go down, when you download the entire LLVM code tree, today you'll get both Clang and Flang. So at some point, I think it's quite reasonable for us to think about providing that compiler on VMS, perhaps alongside the existing compiler. There may be some, in case there are some features that aren't in Flang, you can keep the old compiler, but have a newer compiler in case you had modern Fortran from an open source project or something you're trying to bring over.
Thanks, John. From Don, how difficult would it be for someone outside of VSI to port an open source LLVM compiler to VMS? Oh,
so that was the one we had.
Sorry, wrong place. What has been
I will add to that, if you look at the number of the lines of code that we've changed to LLVM to actually make it work on VMS, it's been less than 500.
From Edgar, what has been your feeling when compiling and working on an Itanium to work with Intel Platinum? Is the difference much?
Intel Platinum. I'm not sure what Intel Platinum is.
Edgar, we'll have to get back to you with that one. Let's go to Robert's question regarding the trampoline routines. Does linker output include information about trampolines to assist in troubleshooting should a problem arise?
Bob, you're reading my mind. So today you can infer where the trampolines are at, but in my humble opinion, it isn't as clear as it should be. In the linker cross references that give all the addresses, it's on my list to try to augment that with additional information. It gets even a little more tricky when you think about in analyze, when you're dumping out the contents of a symbol vector. There's the address of the symbol vector slot, the code in the library, and where the trampoline is. Sometimes there's like 3 addresses you have to print out. But you're right. If you ever had to unravel a mess in front of you, you need them all. So yeah, it's on my list.
Thanks, John. Can I ask what the status of DEC forms is? You can certainly ask.
You can ask. We can. I know, Rob. People. It's been. I think it's on the roadmap somewhere, right?
Yeah, I think. Yeah,
it's been. Stuff has been looked at it because I have had to help people with a couple of questions.
Yeah, Rowan, we'll have to get back to you separately on that one.
Yes. Okay.
Okay, this is a long one from Alistair. Give me some background here. How does
I can read it too, but you can read it out. Yeah.
Yeah, I'll read it out loud for everyone. So, how does the tramp code access data outside of the current 32-bit address space? For instance, 3x 32-bit segments of 2 GB. Your tramp code has execution currently in seg-c and now needs some data in seg-a. Will we need to manually lay out code and copy things to deal with, say, seg-a and seg-c, question mark. Interested in the strategy.
And the answer is no, you have to do nothing. So the linker, so for these trampolines are only for calling routines. Accessing data always goes through the global offset table. And so the linker and that global offset table is at a known distance from each of the code. And I said earlier, we have this global offset table, and it's not per image, it's actually technically per cluster. So if you have something that actually uses the linker cluster mechanism and clusters things together, you'll have multiple global offset tables. The linker manages all of that, much to the loss of the hair of either myself or the former linker developer who's on to something else. The linker managed all that, and the compiler just goes and accesses the pointer to all that data out of the global offset table, and those are 64-bit white pointers, and we'll find it automatically.
John, I'm going to let you do this one. Do you see in the chat box from Don at 10:52? If you don't see it right away,
no,
we'll come back to it. We'll come
okay.
back to it. No problem. Oh, okay. Alistair has commented about the Intel Platinum is a processor set of high-end Xeons, high core count.
The only thing I can say there is that, you know, at this, we fully intend to expose most, all of the Clang command line options. I mean, you can, right now we're running Clang on x86 with a foreign command syntax. And it looks, you can specify any of the 500 and plus options into Clang. I have no idea how many of them work or not, but including asking LLVM to do, you know, very specific enabling micro or, you know, sub-architecture optimizations, whether it's for Skylake or you know, enabling AVX 512 or any of those things. We'll probably, and certainly from the DCL interface on top of any of our compilers, they'll look more like the traditional DCL interface. But at some point, you know, one of my, you know, dreams at night, perhaps it's a nightmare, but I can imagine just running the compilers again as, at least Clang, as a foreign command and get access to every option in there. Not going to test every option in there, but I don't know why I would prevent you from trying it. The worst that would happen is it doesn't work.
John, this is from Gerard. There is an ADA core prototype GNAT ADA on LLVM. Can we try to use it to build an ADA compiler?
Gerard, I know you've been, that's been worked between, I know you and the folks at Ada Core have worked on that. I know people have, there have been discussions, could you try that? I'm sure you could. No, I think there are technical possibilities. I just don't know the product issues. But yes, you can do that.
John, can you see the question in the Q&A section from Helen?
Let's see.
1053.
I'm in the chat box. Where's the Q&A box of these things? Oh, okay. Let's get that over here.
Did you find it?
I'm getting there. Hang on.
If not, I'll go ahead and read it.
Nope, I can. Oh, wow. Okay, I can see it now. So, which ones do we want to do now?
10:53 a.m.
Oh, Helen. So,
yeah.
So, create map section, map global section work exactly the same as they did. So they're 32-bit ones. There are 64-bit versions of those services on Itanium today that you could use if you want P2 space.
And why don't you go ahead and address the one
Okay.
right after it from Don?
And then
go
we
ahead,
have,
go ahead and read
yes,
what's written
so
there.
we have some of our applications have macro32 code that use libdar get current info context, lib current pre-info context, lib info registers. Yeah, are these lib routines available, or will they be? Yes, they are. So on Itanium, there were libdar IA64 underscore get current, same name but with an libdar i64, and we have libdar x86 ones. The difference is if this was coming from, let's say, an alpha platform, info handles on alpha are 32-bit big. Info handles on Itanium and x86 are 64-bit wide. That's the only difference.
And for Mark, can you expand on what you said a short time ago about still needing cross compilers? Our sources C with a tiny bit of macro remaining.
Yeah, I just from my experience of doing software, I mean, you know, my build environment wants CMS. It wants to fetch sources from some, you know, from a TLB. It wants most people who have complicated build environments today, the cross compilers can run on the Itaniums where you have that build environment. If I said you have to now, no more cross compilers, you have to go build natively, you're gonna have to drag all your code over to your x86 machine in some VM instance somewhere, which is an extra step. I just think that it'd be nice to keep the cross compilers for a while to let people do migration from the cross compiler environment to the native compiler environment. I don't see us providing cross compilers forever. As a supported alternative to native compilers.
John, the next question. I built a cross-compiled GCC C++ for Itanium, and I work on the standard lib. Could be useful on the Itanium side of the workshop? Question mark.
Perhaps I have, not for me, I don't need it, but I mean, I don't know, you know, trying to use a GCC C++ on Itanium, let's say, to build a better Clang or a better, newer LLVM on Itanium, possibly. I mean, maybe if my time machine ever gets fixed, I can, you know, I've got, maybe that's a different alternative, but today that's not particularly interesting for me.
And from Philip, do you know if RDB can be compiled on x86 yet?
And I think the answer is you'll have to ask Oracle.
We know that they're working on it.
Yes, we do.
We have regular engineering meetings with them, so we know that they're working on it.
I trade email with them on a regular basis.
Let's see. From Edgar, it looks like a statement. HP DL380 Gen 10 and Gen 9 use this kind of processors.
Yeah.
So obviously to
earlier, John Pinkley asked, is checksum image supported? Yes, it works. I use that. Let's see, backwards, is there never be a binary translator? I think Claire's latest roadmap and the latest webinar talked that there's currently no plans for a binary translator. Let's see, somebody, SCA PCA support. I think that, you know, PCA certainly being a little more architecture aware, but it's certainly a part of the DECset suite that's going to be there. SCA should be there. You can extend the question of, is one of the changes we have to add to Clang to add what you would, you know, an analysis data qualifier? How do you get SCA stuff out of Clang? Well, there's a lot of tools that come in the LLVM world that are equivalent source analysis tools instead of SCA. I mean, SCA is integrated with LSE. From that vintage of tools, they work together, but it's not as modern as some of the other tools that you could get out of, you know, a Clang LLVM based compiler, though that would probably involve more work. I really don't know how it integrates into the IDE stuff that we have from Brett's team. But one of the things that are in the back of my head is Clang has a documented interface to access their abstract syntax tree, AST. So you could write a relatively simple filter that walked down the Clang abstract syntax tree and wrote out an analysis data file. It's essentially the same information, just in a different representation. So somewhere in the back of my mind, I think, yes, we probably can even add the SCA support into Clang, or at least bolt it onto the side.
And John, Don asked a question in the chat box at 10:52 a.m. and I think if you can find it, it would be good to address it. I would let you read it and address it while you look for Sorry, go ahead.
I don't see anything in the chat at 10:52. I see Alistair's asked a question at 10:51, and then Edgar asked at 10:56.
Interesting. Okay. Don, I will make sure you get your question addressed. Just going to make a note
It's
here.
been blacked out or something for me.
Okay. Any future plans for implementing PL1?
Wow, I actually haven't talked about PL1 in quite a while. So no, I don't see, I mean, for many of you know, PL1 has not been owned or managed by, anything with HPE or VSI. That was Kednos with a gentleman named Tom Linden, who actually sadly passed away a year or two ago. I don't know anything about the official legal status of any of that product set. I know some of the people involved, but I don't think anybody's in position to make any statement on that. But you'd have to ask the people who own it, and it's not us.
What is the earliest date you expect to be able to make C++ compiler available?
I don't know if I can pick a date. We're trying really fast. I mean, that's actually,
Yeah.
there's people that's their main goal is to work on that right now. Because that is the piece that's missing. I understand there's a lot of people out there now that are using cross compilers trying to rebuild their application, except they have C++ code and they are stuck. There's no place to compile that code. So this is a place where your choices will be, you're gonna have to compile it natively, bring the sources over, compile it on the x86 box. And then maybe take the objects back to your Itanium and link it with the cross-linker with all the rest of your Fortran and COBOL and C or whatever.
Thanks, John.
So I can't say by 9/1, but I think it's as fast as we can after that. That is probably one of the top things on our list. It's one or two on the list.
It's not fair to set a date at this moment in time.
Yeah.
Okay, possible alternative to binary translation. Perhaps go back to something based on one of the alpha emulators with provision to use trampolines to/from native code.
Bob, that is somewhat interesting. I can imagine there would be, obviously worrying about context, registers and stuff across the boundary. It's possible, I suppose. But at this point, I think there's just, I think, Terry, you have discussed, I mean, the business case versus the technical case of having binary translators.
Yeah. Let's see, there are pieces of X11 which were vested to Alpha and vested to Itanium, ? There will not be a new general revest.
There's no, at this point, no binary translator that's going to take anything to x86. You're going to have to compile it from source. Then somebody asked, where is data retrieve in the porting to x86 64? I have seen actual wombats working on x86, so I think it's in there somewhere. Is there a realistic approximate date for a native Fortran compiler, both the regular one and the Clang one? So our traditional, Fortran native will be one of the native compilers we'll get over the course of the next 6 months inside of the 9.1 release. So the Flang one is probably farther out. I mean, Flang one is the Flang people aren't done with Flang yet. So I'm certainly not going to invest time to chase a vastly moving target. And then speaking of Fortran, I actually have had I've run Adventure on my x86 box, so it works perfectly. If you do all the steps correctly, you will, win the Colossal Cave Adventure without getting eaten by a dwarf.
I don't see any other questions that have popped up.
Okay.
Hopefully we've been able to address as many as possible. If anyone has any other questions.
Absolutely. We saw, just the info at VMS Software. You all can probably extrapolate to my email address of john.reagan@vmssoftware.com. So any questions, you can just write them on the back of a $100 bill and send them to me, and I'll be happy to answer them.
Do you take euros, John?
Yeah, no Bitcoin. It's too volatile.
Okay, a couple comments thanking us. Thank you, everyone. We appreciate your active participation. It's terrific to have such interest in what the activities are at VSI for everyone's for the marketplace. As John just said, please, any other questions, info@vmssoftware.com is a great place to send, and you will get answers to your questions. Our next webinar will be targeted towards the mid to late June timeframe. We are sorting out the topic for that now. If you have any specific topics that you would like to hear, please send us a note at info@vmssoftware.com, and we will certainly put it under consideration, if not for the next webinar, possibly for a future one later this year. We hope that you have a great day. Thank you again for your attendance and participation, and we'll talk again soon. And thank you, John. Take care. Bye-bye.